Do you get happy when you see DNA stained with Dappy? Do you get SYBR Green with envy when you see those QPCR curves? Do you ever run a gel and then stain with Ethidium Bromide to see what's inside? Well, if so, or if not, I hope this post can still be a cyber gold source of information about fluorescent nucleic acid stains, some of the basic principles of fluorescence and fluorescent stains, and these stains in particular, and some different pros, cons, when to use what, and various things about how they work. So let's dive in.
So today I want to talk about these fluorescent nucleic acid stains. This is going to give me the opportunity to talk about some important concepts regarding things like fluorescence, what to look for in a fluorophore, as well as how some of the common nucleic acid stains work and some of the similarities, differences between the ones that you have to choose from. So let us go back to get a broader look. So basically we do some sort of gel electrophoresis to separate DNA or RNA by size. In this electrophoresis, you're using a electrophoretic unit thingamabob to basically create a charge gradient throughout the gel. Your DNA and your RNA are going to have a negatively charged backbone. This negative charge is then going to get them to be attracted towards the positive charge that you create in the gel gradient using that power box. But in order to swim through the gel to get there, they have to actually go through the gel, which is this, basically it's this tangled up mesh. And then you have your strands trying to crawl through that mesh and getting tangled up. And the longer the strands are, the slower they're going to go. And then thus, when you turn off the power, you stop that gradient, remove that positive charge that was getting them motivated to move through the gel. Now they're going to be stuck in place. So they're stuck in place, they're trapped into this gel because they're all tangled up, but you can't see them. They're going to be invisible to you. And so in order to be able to visualize them with something like a gel dock or a UV screen, we need a way to get a dye to bind to them and to then be able to show it to us when we shine light on them at one wavelength, get them to give off another wavelength. And this is the idea of fluorescence, where you shine a light wavelength of one, light of one wavelength at something, and it gives off light of a different wavelength. So we can use a machine like a gel dock, or so like one of these machines or a UV tray. These have different wavelengths that you can set based on the absorbance of fluorophore. And then you can detect, here it's visual detection. Here you can have like inside of this machine, it can detect the different wavelengths. So this is the basic idea about how these stains work, is that you get a molecule to bind to the DNA and then fluoresce. So we'll get more into the exact concepts about how these work. But a couple of important things are that you only want the dye to be fluorescent when it's actually bound to the molecule of interest. And so one of the important things about these dyes is that they're going to fluoresce only, or at least a lot better, when they're actually bound to nucleic acids. Different dyes are going to have different binding preferences, and this will help dictate which one you want to choose, as well as the sensitivity and things like that. But you don't want them to just fluoresce all the time, or else this would give you like a really high background. As to how in practice these work, it's going to depend on the method. So sometimes you soak them in the stain afterwards. Sometimes for like an agarose gel, you can actually put in like in the loading dye, like Easy Vision loading dye, it actually has the fluorescent dye in it, in the sample loading buffer. Or you can use something like Ethidium Bromide or SYBR Safe, where you can actually make the gel in it. You can add some to the gel when you're making it, and therefore you don't have to stain the gel afterwards because it's already in the gel, or you can also stain the gel afterwards. So there are different methods to do these different things, but typically you're not doing anything to kind of like wash everything out. So you might be used to like a protein stain if you're doing some sort of like classical chromatography where you have to do a bunch of destaining steps because you have the dye everywhere. Here, you still have the dye everywhere basically, but it's only going to be fluorescent. It's only going to give off that light when it is bound to the nucleic acid. So in order to understand why this is, we need to kind of better step back and understand how fluorescence works. So as I mentioned, it involves absorbing light of one wavelength and giving off light of another wavelength. So first off, what is light? Light is electromagnetic radiation, or EMR. We often think of light as being visible light, but visible light is only a tiny little slice of the electromagnetic radiation spectrum. And what all of this light is, from gamma rays, which are really, really high energy, all the way through X-rays, ultraviolet, visible, infrared, microwave, and radio waves, these are going to be lower energy, longer wavelength. All of these has in common is that you have basically these little packets of energy called photons, and these are traveling in these waves, and we can characterize them based on the energy of the photons, which directly correlates to the speed of the wave and like the distance between the waves or between the peaks, so the tops, these peaks. So basically, you can think of it kind of like a grandpa and a little kid going on a walk together. They're both going to be traveling at the same like linear speed, but the kid might be like running around the grandpa all the way to get there. Or you can also think of like a slalom race where if you have like a bigger S or a smaller S. So the little kid's spending a lot more energy because it's running around more, but it's still going at the same like overall rate as the grandpa. And so this is something similar to light, and that light is all going to travel at the same speed, the speed of light. But if you have more energy in your photon, you're going to be traveling faster. So you're going to go more up and downs for each, for the same linear amount. So the higher the energy of the photon, the shorter the wavelength, and the higher the frequency. So the frequency, like how many times would you see this? And if you had like a wave, how many times would it be hitting? And the more times it's hitting, the shorter the wavelength because it has to go the same overall speed. So you can think about higher energy, higher frequency, shorter wavelength, lower energy, lower frequency, longer wavelength. As for the amplitude, that's just talking about like how high it is, like how strong it is basically. So we have all these different kinds of light. Although our eyes can only like make out this visible light spectrum, we have this ultraviolet light over here. That's still, it's still light, and we just can't see it. And these fluorescent molecules, a lot of times what they do is they absorb this ultraviolet light and then give it back to us as visible lights that we can see. So in order to understand how this works, let's talk a little bit about why molecules actually absorb light in the first place. What's actually happening when a molecule absorbs light? And this goes back to the idea of electrons and electron orbitals. So basically, all molecules are made up of atoms, like individual carbons, oxygens, hydrogens, nitrogens. And each of those is made up of smaller parts, these subatomic particles. And so you have this central nucleus where you have positively charged protons, neutral neutrons, and these are all hanging out in this really dense core. And then around this, you have this sea of negatively charged electrons. And these molecules or atoms can share pairs of electrons to form bonds. These electrons, they're in this cloud whizzing around, and we can never actually know exactly where they are, but we can kind of characterize them based on how they act, and where they're most likely to be. And so they're actually in these weird like shaped orbitals and stuff, but it's often we think about them as kind of being in shells. And you can think about electrons as being in different energy states. So the lowest energy state is going to be like the ground state, but these electrons can absorb energy, such as energy from those photons from light, and then this can excite them when they get excited to this excited state. When they get like absorb this energy, they get promoted to an excited state, but it's hard to stay in that excited state. And so it ends up going back to that lower energy ground state. When it does so, it's going to have to give off that energy that it absorbed. But because it's not totally efficient when it does this, there's a little like vibrational relaxation and things like that. You have some like non-radiative emission, so that it's basically things that aren't giving off light, but they're still releasing a little energy. So therefore, the light that you give off is going to be usually have a lower energy wavelength. So going back to our idea of electromagnetic radiation and how we have ultravisible light, ultraviolet light here, and then we have our visible light here. So this is going to be higher energy. So a molecule can say absorb ultraviolet light and then give it off as visible light. And this is what we see in some of our nucleic acid stains, is that they're absorbing light from over here in this UV region and giving it back to us as visible light that we can then observe, such as on one of these UV trays. So in terms of what wavelength that something absorbs, so not all molecules are going to absorb the same wavelengths. What wavelengths they absorb is going to depend on the distance between like the ground state and the excited state. So the photons that we talked about with the light, those are discrete, like quanta or whatever. Basically, they have specified energies. So it's not like a gradient in between. Well, I mean, it's kind of like, but each wavelength has, the photons in that wavelength have distinct energies. These little like packets of energy. And so the packet of energy has to be exactly right in order to match the distance between these two states. So I say exactly right, but there's actually a little bit of wiggle room because there are these like vibrational levels within these different excited states, and it gets a little bit confusing. But basically this makes it so that there's a place, like it'll have a maximum absorbance where it's like the most perfect amount to absorb to get to the next level. But then you also have, because of that wiggle room, you're going to have more of like a bell curve in the absorbance as well as the emission due to this. When you have a fluorophore, it's going to have an absorbance and it's going to have an emission. It might have more than one absorbance because different parts of a molecule can have different, absorb different parts of light, because the distance between these levels and therefore the energy of the light that's required in order to promote those electrons is going to depend on the electrons like environment. So this is basically the electron of that atom isn't just hanging out on its own, it's also connected to other molecules, and different parts of the molecule, there'll be different electrons. So basically you can have dyes, you can have various things that have multiple absorbance, emission, and absorbance, and even emission spectra or peaks, maxima. And this is going to, the difference between these, so basically you don't want there to be a big overlap between your absorbance and your emission, or else it's going to be hard to measure your emission without actually measuring the light that you're shining on there as well. And so the distance between the absorbance and the emission is going to be the Stokes shift. And so one of the things that you want to look for in a fluorophore is going to be having a good Stokes shift. I guess I don't have that on this slide, but that's one of the things you want, is you don't want there to be a lot of spectral overlap. This also applies if you're using multiple fluorophores, you don't want them to have overlapping emission spectra. But that's not really coming into play in this case. So different parts of a molecule can absorb photons differently and absorb different energy levels. In order to absorb this energy, often molecules are absorbing energy that we just can't see. And it's either too high energy or it's too low energy or something like that, and it's not really useful. Sometimes we actually do see colored compounds though, and a reason why we often see colored compounds is because the molecules have some sort of resonance or aromaticity. So resonance is when you have atoms, more than two atoms are sharing electrons, and so you have some like this kind of electron commune where you have multiple atoms sharing electrons. Like barely with all of them instead of just two sharing a pair. And when it happens in a ring, we call these molecules aromatic. When you have resonance, it's going to decrease the distance between these the states, and this is going to make it so that you need lower energy light in order to actually see it. And so these molecules can say absorb visible light, and if something absorbs visible light, it's kind of stealing a slice of the rainbow, and therefore you see a color. Because you see if white light has all the colors of white, now you're taking color away. Now you're going to see the leftover, which isn't going to be the same color. And so this is why some colored compounds look colored. When you have a molecule, dye molecules often have these sorts of aromatic groups as well, because this is going to help them better absorb light that is in a range that's going to be helpful to us. And so these molecules often expect them to have some sort of aromatic group. And these aromatic groups, as you'll see in these couple examples, a lot of times for our nucleic acid stains, these groups are also going to have this like flat or planar property that's going to help them bind to the DNA or RNA. Either you can often these bind intercalating, such as like Ethidium Bromide. You can see it's kind of like this flat nature is actually getting it to like wedge itself or like kind of slide in between the rings of the ladder of the DNA. And then you can also have like in the minor groove. So basically DNA has this minor groove, which is the smaller groove, and then the major groove, which is the bigger groove. And like Dappy, this dye we'll talk a little bit more about, it can bind in the minor groove, especially in an AT-rich region. So it's binding over here. If you look at the GC or CG, so you have these groups that are going to this like the G's, it's got this NH2 group, and that's going to kind of like stick out into that groove and make it uncomfy for the Dappy. But AT regions are good for the DAPI, and this is going to allow you to bind to the DNA. And then if you have this absorbance and you shine light at this wavelength, then you can then measure light at this wavelength. And so then you can use this to say in fluorescence microscopy in order to detect where the nuclei are located in cells. So those are just a couple examples, and we'll get into more details. Okay, so the basic idea though is that we are going to absorb light at one wavelength and give it off at one wavelength, a different wavelength. But that's not all of that we care about in a fluorophore, especially if we're using it for a stain. So if we're using it for a stain, we want to make sure that it's very sensitive so it can detect low levels of something. And so we'll see that the different stains have different levels of sensitivity. And we also, it's really, really important that it has high specificity. So we don't want background from non-specific signal. And so we don't want it always shining. We only want it to, or always giving off light when we shine that wavelength at it. We only want it happening when it is bound to the thing of interest. And so how this works is that when you have a molecule, when you have a dye molecule actually binding to the DNA or RNA, it's actually going to change the electronic environment. So remember, the electrons are what's going to be absorbing the energy. And if you have the, when the electrons are in a different environment, they're going to have different energies that need to be, like the distance between those different states is going to differ. And so, for example, when the Ethidium Bromide wedges its way in here, now you have these actual interactions. So that you have this base stacking in DNA or RNA between like these different rings of the ladder, the rungs of the ladder. When Ethidium Bromide gets in there, well, now it's going to kind of sync up with those rings in this like base stacking and stuff. And basically it's just going to change the electronic environment and change the wavelength at which it's going to best absorb at. So now it's going to absorb at these wavelengths, which you can then shine light on. And similarly with DAPI, so basically in all of these cases, the binding is going to change the energy levels that are the energy that's required to move between those different energetic states. And this is going to allow you to only have the absorption and only have the fluorescence when the molecule is bound. So these are important things that you want to make sure that you have in your fluorescent stain. In terms of fluorophores in more general, there are also things that you care about, like how well they work in general. The extinction coefficient is basically when light hits, how much is absorbed. So basically, although we know that it'll absorb this wavelength, say, how efficient is it actually? So if you shine a bunch of light on it, sure, it could take that energy, but how likely is it to actually do it? And if it actually does it, how much of it is likely to get re-emitted? So as we talked about, there are some ways that you can kind of like fizzle out and give off energy, so just like bumping into other molecules, giving off heat, that sort of thing, rather than giving off light. And so if what we care about is the light, we care about this quantum yield, which is of the light that's absorbed, how much actually gets re-emitted. I think for SYBR Gold, it was like 0.6 or 0.7 or something, but I'm not exactly sure of all of them. Okay, and then there's photostability. So how long can it keep doing it, absorbing and emitting and absorbing, emitting, absorbing, emitting? So there's this thing called photo bleaching where fluorophore kind of gets like stuck. If you use it too much, it can get stuck in this like state where it's like not going to be this like forbidden state and all this weird physics stuff, where basically it's not going to be useful anymore. And so that's why you have to protect it from light when you're using these stains. You typically cover them in foil or keep them in the dark, that sort of thing. And so you want your stain to be photostable. So these are some of the things that companies might be talking about when they're like advertising their different products. So let's talk about some of these different products and some of the times we use them. Okay, so when it comes to like agarose gels, the most common or like the classical method is Ethidium Bromide, sometimes abbreviated EtBr. So this is going to work best for double-stranded DNA. And when I say work best, I mean like it works better for that than it does for anything else, but it's not the best stain. It has a pretty low sensitivity, which is its biggest problem, well, that and a PR problem. So basically, it's an interpolator, so it's going to stack between the bases. When you have something like this, it has the potential to act as a mutagen. So a mutagen is something that is going to have the potential to cause mutations. In our bodies, if a mutation occurs in DNA, this mutation doesn't get fixed. It can then cause the cells to have mutations, and this can cause things like cancer. But our cells have a lot of machinery in order to help fix mutations. And in fact, we have mutations happening all the time because of things like UV, various things like that. Our DNA has a lot of machinery in order to fix these mutations. So if we measure, typically mutagenicity is measured using something like an Ames test, which is done in like bacteria, and it's looking for bacterial revertance. And I have a post on this test. It's kind of a cool test, but it's done in bacteria. And it's not like telling you what's actually going on in the body. So just because something can act as a mutagen in the lab does not mean necessarily that it can cause cancer. So if something causes cancer, we call it carcinogenic. If something can cause a mutation, we call it mutagenic. So some mutagens are carcinogens, but not all mutagens are carcinogens. So because Ethidium bromide can cause mutations in the lab, so it's mutagenic in this sense, it got a very bad reputation from the very start. But apparently studies in animals haven't borne out the idea that it's really this toxic. And according to this article, a 50-kilogram researcher would need to drink 50 liters of gel staining solution to get even the non-toxic dose using cattle. So it's actually been used in cattle as like a drug, and used for like sleeping sickness and various things like that. So basically, a lot of companies have kind of capitalized on this bad reputation for Ethidium Bromide in order to sell their things as safer, but it's not necessarily that those things are actually safer, and sometimes these newer compounds actually have a lot less studying done on them. So the bottom line is that you should not go drinking Ethidium Bromide. That's not at all what I'm saying, but you should take precautions whenever you use any of these things, that you're wearing gloves, you are disposing of things properly, you're not like doing things and then like eating with your dirty hands, you're washing hands, various things like that. But don't be like terrified of it, especially compared to other stains. But it does have relatively low sensitivity. Another kind of, so this one you often use by like either putting it in your dye putting it in your gel before you run it, or by like staining your gel in the dye afterwards. Another one that's commonly used in this manner is like SYBR Safe. Again, I don't know how much safer it actually is, but things like that. Another common DNA stain that I mentioned before is Dappy. So Dappy is going to be one of these minor group binders, and it's going to have a maximum absorption at 358, so kind of purpley, or kind of in this UV range, and then this maximum emission at 461, so a more blue or light. This is often, as I mentioned, it's actually used to stain nuclei in fluorescent staining, because it binds to double-stranded DNA. And so both of these have about a 20-fold increase in fluorescence when they bind to the double-stranded DNA. So it's not nearly as good as like SYBR Gold, which is going to have about a 1,000-fold increase in fluorescence when it binds to nucleic acid, but you still have some differential activity when it's bound to the double-stranded DNA. So you have less of a background than if it didn't have any change. So as I mentioned before, it binds to the minor groove, especially in these AQ-rich regions where there's not that amine group from the G sticking out and making it uncomfy. When you have it, so this is used in like this easy vision dye that I've used a lot, which is actually in the sample loading dye, as well as like just dyes, like tracking dyes, so that you can see the progress of the various size things in the lanes. So these are the visual dyes, but then you also have the fluorescent dye, which is the DAPI based dye, this easy vision that you can then see with the UV. So putting in the loading dye is really useful, because then you don't have to stain or anything like that. So that's that. And then finally, let's get to the SYBR stains. So SYBR is like a proprietary name or something. And there are a couple of different varieties. There's debate over how they bind. It's likely some sort of mixed mode. So some people say they circulate, some people say it binds a groove, some people say it's a mixture. So I'm not going to go down that rabbit hole any further. Instead, I'll just tell you about some of their properties of a couple of the main ones, SYBR Green and SYBR Gold. So SYBR Green has good selectivity for double-stranded DNA, which makes it useful for real-time detection of QPCR products. So QPCR, quantitative PCR, is basically where you run PCR to make lots of copies of a region of interest of DNA. You can also do like RT QPCR. So sometimes RT stands for real time, sometimes it stands for reverse transcription. Sometimes you see like RT QPCR, like reverse transcription, real time reverse transcription, I don't know. But basically there you start with mRNA or some sort of RNA, and then you turn it into DNA and then measure it. And so this could be used to like measure gene expression. But you can also use qPCR just to measure some sort of DNA that's originally present. The basic idea is that each cycle of PCR, you're going to be doubling the amount of that sequence present. And when you double the amount of that sequence, you're also doubling the amount of double-stranded DNA. So if you use a dye that binds specifically to double-stranded DNA, then you can measure the fluorescence of the molecule, fluorescence of the solution over time. So because these dyes are going to have an increased fluorescence when they bind to double-stranded DNA, now they're going to tell you about the quantity of double-stranded DNA in your solution. The more copies you have, the more, the stronger the signal, the more copies you start with, the faster the signal will grow. And therefore you can measure like the cycle threshold or like CQ value, or like the number of cycles it takes to get past the threshold. And the more copies you start with, the fewer cycles it'll take, and the lower the CQ or the CT number. So this can have, so you'll see something like this. So SYBR Green is often used in QPCR as one of these like double-stranded binding dyes. A problem is that because it binds to every double-stranded DNA, it's specific for double-stranded DNA, but any double-stranded DNA. So it's not necessarily these products. So you could have like a totally messed up product, like a totally different product, a totally off-target product. You could have primer dimers, various things like that. So there are methods that use like a probe, and this fluorescent probe is then going to bind to these sequences. So instead of binding to the double-stranded DNA, it actually binds to the anneal step where these separate. So it'll bind like here, and then when the polymerase actually moves, it's going to kind of like chew up these things, and basically these are primers, so they have a fluorophore on one end, a quencher on one end, and when this probe is intact, the quencher is going to quench the fluorescence. So instead of that energy being given off as light, it's going to be given off like non-radiatively and actually get captured by the quencher. But when this polymerase again chews it up, when it runs into it, then it's going to separate those, and you actually see this fluorescence. And so because you design these probes so it binds on the product, this is going to give you a more specific readout. But if you have to design these probes for every single reaction, what you do when you have one of these double-stranded DNA binding dyes, then this can be used just like for any reaction, and you can have just like a master mix, like a SYBR Green master mix based, or SYBR Green based master mix. And so this was what I was using the other day when I was doing my thing. And so in order to kind of get a little sanity check that I had about what was in there, you can actually do like melt curves where you look to see basically the melting temperature is like when the strands are together. This does like a temperature gradient to see how long it takes in order for like how high in temperature you need to get in order for the strands to come apart. And remember, because this dye binds to double-stranded DNA, when those strands come apart, then you're going to get a loss of fluorescence. And so you can see that you have a high fluorescence at these lower temperatures when the strands are together, but then as you go up in temperature, the strands can come apart. And when they come apart, then you're going to see a drop off in the fluorescence. Based on the slope of this line, it tells you about the relative melting temperatures of different things in your solution. So sometimes if you have like two peaks, I can tell you that there are two products, but it could also just mean that you have like your piece has parts that are more tightly bound and parts that are more weakly bound. So say like more GC rich region and a more AT rich region. These regions are going to, so you kind of, when you're melting, you're going to have it be biphasic. And so like part of it's going to reduce faster or slower because the dye is like bound all along. And if part of it's still double-stranded, or part of it single-stranded. Basically, it's not as simple as it might seem that, oh, you have two peaks, you have two products. Not necessarily. And so there's actually, you can do various things to predict the actual, there's like software you can use to predict the actual melting curve and things, but it can be used as some sort of indicator, but also if you run a gel, you should be able to see if there are really multiple products. The one that I use a lot, such as what I was using yesterday, is the SYBR Gold. This has the highest sensitivity. It can detect as little as a nanogram of RNA or 25 picograms of DNA. So it's also very versatile. So it can detect RNA, double-stranded DNA, or single-stranded DNA. It comes as like this 10,000-fold little vial. What they do here, which is really helpful, is they make little, like, we have a little 5 microliter aliquot. So you just stick a 5 microliters of that and 50 mils of your like TAE or TBE of your TBE solution that you ran the gel in. And then you don't have to keep freeze thawing it. These dyes have two choices of excitation wavelength. So about 300 nanomolar, which is in the UV range. So you can use like one of the, like a UV table, or you have also like about 495, which is in the blue range. So you can use like a blue light table. And then it's going to emit about 537, so like in the green range. And you're going to have about 1,000-fold increase in fluorescence when it binds to nucleic acid. So this makes it really useful in like having the low background and so because you have something that's so sensitive, you want to make sure that it's not just giving off fluorescence all the time. So it's great if it's sensitive that like anytime there's DNA or RNA, you'll get a signal, but you only want to make sure that you get the signal if there's DNA or RNA. So you could have something that's like 100% sensitive, but it just like gives a signal all the time. So if you're giving a signal all the time, well then yeah, if there's DNA or there's RNA, it's going to give a signal. But if it's you want also there to be selectivity so that if it's not there, then you're not getting a signal. And so this is the basic. So this is why this, because you get that 1,000-fold increase in fluorescence when it binds to nucleic acid, this is going to make it very selective as well as being very sensitive. I do not work for the companies that sell any of these. These are just some of the products that I've used in the past. And I hope that this post helps you understand fluorescence and the basics of these different fluorescent dyes.